The instruments did not fail, they began to agree. Across multiple monitoring stations, magnetometers that typically trace smooth, predictable oscillations in Earth's magnetic field started recording irregular pulses. The variations were not extreme, they were subtle, shifts of tens of nanotesla within a field that averages about 25,000 to 65,000 nanotesla, depending on location. But the pattern changed. The signals became more structured, more persistent, and, in a measurable sense, louder. At the same time, ionospheric sensors detected unusual fluctuations in electron density at altitudes between 80 and 600 kilometers. These variations appeared in March, during a period when solar activity was elevated but not exceptional. The expectation had been routine disturbance. What emerged instead was coherence across systems that usually respond independently. The implication is not immediately obvious. The question is precise. Why did Earth's atmospheric shield begin to behave as if it were being driven differently? If you are ready, join us as we trace the signal through the layers of the atmosphere and into the processes that sustain it. Let's begin. Most descriptions of Earth's protective layers divide them into separate systems. The atmosphere blocks radiation, the magnetic field deflects charged particles, the ionosphere reflects radio waves. These descriptions are accurate but incomplete. In reality, these layers operate as a coupled system, exchanging energy continuously. Imagine standing inside a building during a storm. The roof blocks the rain, the walls slow the wind, the internal structure absorbs vibrations. Each part has a role, but none operates in isolation. When the storm intensifies, the entire structure responds. Small changes in pressure or force can propagate through beams and surfaces, creating patterns that were not visible under calm conditions. Earth's shield behaves in a similar way. Solar radiation, charged particles, and electromagnetic waves interact with the magnetosphere, ionosphere, and upper atmosphere simultaneously. Energy enters the system primarily from the sun, carried by the solar wind, a stream of charged particles traveling at speeds between 300 and 800 kilometers per second. When this flow encounters Earth's magnetic field, it is redirected, compressed, and sometimes partially absorbed. The common assumption is that this interaction is chaotic but averaged. Over time, fluctuations smooth out and the system returns to equilibrium. But this assumption overlooks the fact that the system can enter states where energy transfer becomes more efficient, more synchronized. In those states, small inputs can produce disproportionately organized responses. To understand the scale of this interaction, begin with your immediate environment. The air around you exerts a pressure of about 101,325 pascals at sea level. That pressure results from a column of air extending roughly 100 kilometers above the surface. Most of that mass is concentrated in the lowest 10 kilometers where weather occurs. Above this lies the thermosphere, extending from about 80 kilometers to 600 kilometers in altitude. Temperatures here can reach 2,000 degrees Celsius, not because the air is dense, but because individual particles carry high energy. Beyond that, the exosphere gradually transitions into space. Now extend outward to the magnetosphere, which is not defined by air, but by magnetic influence. On the side facing the sun, it extends to about 65,000 kilometers. On the night side, it stretches into a tail that can exceed 6 million kilometers. This region contains charged particles trapped and guided by magnetic field lines. Beyond this lies the solar wind itself, originating from the sun's corona, which has temperatures exceeding 1 million degrees Celsius. The distance from Earth to the sun is about 150 million kilometers, and yet the effects of solar activity are felt within minutes to hours through changes in particle flux and electromagnetic conditions. At each step outward, the scale increases, but the connection remains. A fluctuation in the solar wind can alter the magnetosphere within tens of minutes. That change can propagate into the ionosphere within seconds. The system is vast, but the connection is immediate. Measuring these interactions requires instruments capable of detecting extremely small changes across large distances. Ground-based magnetometers can detect variations as small as 1 nanotesla. Satellites such as those in low Earth orbit carry plasma analyzers that measure particle densities down to a few particles per cubic centimeter. The challenge lies in separating signal from noise. The ionosphere, for example, is influenced by solar radiation, Earth's rotation, atmospheric tides, and geomagnetic activity. Each of these factors introduces variability. To identify a coherent pattern, measurements must be synchronized across locations and altitudes. This is achieved through networks of sensors distributed globally, combined with satellite observations that provide vertical profiles. Data is time-stamped with precision down to milliseconds, allowing correlations to be identified. When multiple instruments detect similar patterns within narrow time windows, the likelihood of a genuine signal increases. The design decision that enables this is redundancy. Instead of relying on a single measurement, the system compares dozens, sometimes hundreds, of independent observations. The result is not a single trace, but a composite image of how the system behaves over time. And then there is the waiting. Instruments remain active continuously, recording fluctuations that may or may not align. The data accumulates slowly. Patterns emerge not from isolated events, but from persistence. The system listens. What scientists expected to observe during March was consistent with the rising phase of the solar cycle. Solar activity follows an approximately 11-year cycle with periods of increased sunspot numbers and solar flares. During these periods, the solar wind becomes more variable and geomagnetic activity increases. The expectation was a series of disturbances, short-lived spikes in geomagnetic indices like Kp, which ranges from 0 to 9, and DST, which measures changes in the ring current around Earth. Typical moderate disturbances might produce Kp values of 4 to 5 and DST variations of -50 nanotesla. What was observed differed in structure, not magnitude. Instead of isolated spikes, there were extended intervals where fluctuations exhibited quasi-periodic behavior. Frequencies in the range of 1 to 10 MHz became more pronounced, corresponding to oscillations with periods of 100 to 1,000 seconds. To make this concrete, imagine constructing a building where each floor is added one at a time. Under normal conditions, the process is steady. Each level is completed independently. Now imagine instead of independent steps, the entire structure begins to oscillate as floors are added, with vibrations passing through the frame. The building still rises, but the process is no longer isolated. It is coupled. In the atmospheric system, this coupling appeared as synchronized variations between the magnetosphere and ionosphere. Electron densities at altitudes of 300 kilometers fluctuated in phase with magnetic field variations measured on the ground. The amplitude of these fluctuations was modest, changes of 10 to 20% in electron density, but the coherence was unusual. One possible explanation is enhanced solar wind driving. If the solar wind carries periodic structures, such as pressure pulses or magnetic field rotations, it can impose oscillations on the magnetosphere. These oscillations can then propagate along magnetic field lines into the ionosphere. Data from upstream solar wind monitors indicated variations in dynamic pressure on the order of 1 to 3 nanopascals, with periodic components. However, the frequency and persistence of the observed atmospheric response exceeded what would be expected from these inputs alone. Another explanation considers internal resonances. The magnetosphere can support standing wave modes, known as field line resonances, where oscillations occur at natural frequencies determined by magnetic field strength and plasma density. These frequencies often fall within millihertz range. If external driving aligns with these natural frequencies, resonance can amplify the response. The system effectively rings, sustaining oscillations longer than the initial input would suggest. This could account for the coherence observed across multiple layers. However, modeling indicates that the observed spatial extent of the oscillations, covering latitudinal ranges of several thousand kilometers, would require a level of synchronization that is not easily achieved through resonance alone. The system appears to be responding as a whole. There is also the role of atmospheric tides, large-scale waves driven by solar heating that propagate upward from the lower atmosphere. These tides can modulate ionospheric densities with periods of 12 or 24 hours. Interactions between these tides and geomagnetic activity could produce complex patterns. Yet the frequencies observed in March were shorter, on the order of minutes rather than hours. While tides may contribute to background conditions, they do not fully explain the higher frequency coherence. The result is a layered discrepancy. External driving is present but insufficient. Internal resonance is possible but incomplete. Atmospheric coupling is relevant but does not match the observed timescales. Each explanation accounts for part of the behavior. None accounts for all of it. The system is not behaving randomly. It is organizing. This persistence suggests that the atmospheric shield, composed of magnetic fields, plasma, and neutral particles, can enter states where energy transfer becomes more efficient across layers. These states may be rare, or they may be more common than previously recognized, but difficult to detect without coordinated measurements. The implication extends beyond March. If such states occur, they could influence how energy from the sun is deposited into Earth's environment, affecting satellite drag, radio communication, and even the dynamics of the upper atmosphere. More broadly, they indicate that the boundary between Earth and space is not a static barrier. It is a dynamic system capable of transitioning between modes of behavior. When viewed in the context of the larger universe, this system is one example of a more general principle. Energy flows through structures, and under certain conditions, those structures organize the flow into coherent patterns. The same mathematics that describes waves in the magnetosphere also describes oscillations in plasmas around distant stars and within interstellar space. The scales differ, but the behavior is connected. There is a counterintuitive fact embedded in this. The energy density of the solar wind near Earth is extremely low, on the order of 1 nanopascal of pressure. This is less than 1/1000th of the atmospheric pressure at sea level. And yet, through coupling and resonance, this tenuous flow can influence a system extending tens of thousands of kilometers around the planet. Small inputs, large systems, organized response. In the distant future, as the sun evolves into a red giant over the next 5 billion years, the solar wind will intensify and expand. Earth's atmosphere may be stripped or altered beyond recognition. The protective shield we observe today is temporary, sustained by conditions that will not persist indefinitely. Even before that, over tens of thousands to millions of years, changes in Earth's magnetic field, such as reversals that occur irregularly every 200,000 to 300,000 years, will alter how the planet interacts with solar activity. The shield is not fixed, it evolves. There is also a limit to how well we can observe this system. Instruments provide data with increasing precision, but they sample only parts of a system that extends across vast distances and multiple layers. Some interactions occur at scales or locations that are difficult to measure directly. This introduces uncertainty, but also a boundary. There are aspects of the coupling between Earth and space that may remain partially unresolved, not because they are unknowable in principle, but because they require observations that are difficult to obtain simultaneously across all relevant regions. And beyond Earth, similar processes occur around other planets, stars, and astrophysical systems. The principles are the same, but the conditions vary. We observe one instance in detail, others remain distant. The atmospheric shield is not silent, it is continuously responding, adjusting, and at times organizing into patterns that reveal how energy moves through space. In March, those patterns became clearer, not louder in volume, but more structured in form. And in that structure, the system reveals itself not as a barrier, but as a dynamic interface between a planet and its star. The signal, once isolated, begins to reveal a second layer of structure that does not appear in the raw measurements. When the time series from magnetometers and ionospheric sensors are transformed into frequency space, distinct bands emerge. These are not continuous spectra. They are concentrated ranges, often centered around 2, 4, and 8 millihertz, corresponding to oscillation periods of approximately 500, 250, and 125 seconds. The pattern is not random, it suggests preferred modes. This is the signature of a system that supports standing waves. To understand this in concrete terms, consider a string fixed at both ends. When plucked, it does not vibrate arbitrarily, it oscillates at specific frequencies determined by its length and tension. These are its natural modes. Energy introduced into the system is distributed across these modes, and under certain conditions, one mode can dominate. Now replace the string with a magnetic field line extending from the northern hemisphere to its southern hemisphere, passing through the magnetosphere. The length of this line can be tens of thousands of kilometers. Plasma density along the line determines how fast waves propagate. The result is a set of natural frequencies, analogous to harmonics on a string. Measurements indicate that these field line resonances fall within the observed millihertz range. The implication is that the magnetosphere is not simply responding to external forcing, it is selecting and amplifying specific frequencies based on its internal structure. There is a delay embedded in this process. Energy from the solar wind reaches the magnetosphere in minutes, but the establishment of a resonant mode can take longer. It requires repeated input at the right frequency, allowing energy to accumulate. This is similar to pushing a swing. A single push has little effect. Repeated pushes at the correct interval increase the amplitude. During the March observations, the persistence of oscillations suggests that the driving conditions remained aligned with these natural frequencies over extended periods. This alignment is not guaranteed. It depends on both the properties of the incoming solar wind and the state of the magnetosphere at that time. There is also evidence that these oscillations propagate downward. Field line resonances can couple into the ionosphere, where they modulate currents and electric fields. These, in turn, influence electron densities and temperatures. The coupling is not uniform. It depends on latitude, with stronger effects observed at mid to high latitudes, where magnetic field lines are more vertical. At altitudes around 300 kilometers, electron density can vary from 10 to the 11th to 10 to the 12th electrons per cubic meter. During the observed events, fluctuations of up to 15% were recorded within minutes. These changes affect the refractive properties of the ionosphere, altering how radio waves propagate. This has practical consequences. High-frequency radio communication, which relies on ionospheric reflection, can experience phase shifts and signal fading. Satellite-based navigation systems, which depend on precise timing, can incur errors due to changes in signal delay as it passes through varying electron densities. These effects are measurable. A delay of just 10 nanoseconds in a navigation signal corresponds to a positional error of about 3 meters. During periods of ionospheric disturbance, delays can vary by tens of nanoseconds, introducing errors that must be corrected. The system, therefore, is not only dynamic, it is coupled to technologies that operate on timescales of nanoseconds and distances of meters, even though the driving processes occur over thousands of kilometers. There is a geometric analogy that clarifies this coupling. Imagine a network of interconnected beams forming a large structure. Each beam can vibrate, but they are connected at joints. When one beam oscillates, it transmits motion to others. Under certain conditions, the entire structure can resonate, even if the initial force is applied at a single point. The magnetosphere and ionosphere form such a structure. Magnetic field lines act as connections, transmitting energy between regions. The result is a system where local disturbances can produce global responses. There is also a boundary condition that becomes important. The ionosphere is not a perfect conductor. It has finite resistance, which dissipates energy. This damping limits how long oscillations can persist. However, if energy input continues, the system can maintain a quasi-steady oscillatory state. During March, the data suggests that such a state was achieved intermittently. Oscillations persisted for periods of tens of minutes to hours, indicating a balance between input and dissipation. Another layer of complexity arises from the interaction between hemispheres. Magnetic field lines connect the northern and southern hemispheres. Oscillations can propagate along these lines, linking regions separated by thousands of kilometers. Observations show that signals detected in one hemisphere often have corresponding signatures in the other, with slight delays corresponding to propagation times. These delays are on the order of tens of seconds, consistent with wave speeds of several hundred kilometers per second along field lines. The system is not instantaneous, but it is coherent across global scales. There is also the influence of Earth's rotation. As the planet rotates at approximately 0.465 kilometers per second at the equator, different regions move relative to the incoming solar wind. This introduces variations in how energy is deposited across longitudes. Over time, these variations can interact with resonant modes, producing patterns that drift or evolve. This creates a layered temporal structure. Some variations occur on timescales of seconds to minutes associated with resonances. Others occur on timescales of hours associated with rotation. Still others occur on timescales of days associated with solar wind conditions. The observed anomalies are not confined to a single timescale. They span multiple layers, indicating interactions between processes that are usually treated separately. There is also a statistical perspective that reveals something subtle. When the distribution of fluctuation amplitudes is analyzed, it does not follow a simple Gaussian distribution. Instead, it exhibits heavier tails, indicating a higher probability of larger deviations than would be expected from random noise. This suggests that the system occasionally enters states where larger responses are more likely. Such behavior is characteristic of systems near criticality, where small changes can produce disproportionately large effects. The magnetosphere-ionosphere system may operate near such a state under certain conditions. This does not imply instability in the sense of collapse, it implies sensitivity. The system is poised in a way that allows it to respond efficiently to inputs, but also makes it susceptible to organized fluctuations. There is a final aspect that connects these observations to a broader framework. Plasma, the state of matter that dominates the magnetosphere and ionosphere, is inherently capable of supporting waves and instabilities. These include Alphin waves, magnetosonic waves, and various drift instabilities. Each has characteristic frequencies and propagation properties. The observed oscillations align most closely with alphenic modes, where magnetic tension acts as a restoring force. These waves travel along magnetic field lines and can couple to particle motion, transferring energy between fields and plasma. The presence of these modes is not new. What is notable is the coherence and persistence observed during the March period. It suggests that the system was not only supporting these waves, but organizing them into sustained patterns. This brings the discussion back to the initial observation. The instruments did not detect stronger signals, they detected more organized ones. The atmospheric shield did not become louder in amplitude alone, it became structured in time and space, revealing modes of behavior that are present but often obscured by variability. The system, in effect, revealed its underlying architecture. And once seen, that architecture suggests that the boundary between Earth and space is not merely a shield, it is a resonant system capable of storing, transferring, and organizing energy across scales that extend from meters to thousands of kilometers.
There is a geometric analogy that clarifies this coupling. Imagine a network of interconnected beams forming a large structure. Each beam can vibrate, but they are connected at joints. When one beam oscillates, it transmits motion to others. Under certain conditions, the entire structure can resonate, even if the initial force is applied at a single point. The magnetosphere and ionosphere form such a structure. Magnetic field lines act as connections, transmitting energy between regions. The result is a system where local disturbances can produce global responses. There is also a boundary condition that becomes important. The ionosphere is not a perfect conductor. It has finite resistance, which dissipates energy. This damping limits how long oscillations can persist. However, if energy input continues, the system can maintain a quasi-steady oscillatory state. During March, the data suggests that such a state was achieved intermittently. Oscillations persisted for periods of tens of minutes to hours, indicating a balance between input and dissipation. Another layer of complexity arises from the interaction between hemispheres. Magnetic field lines connect the northern and southern hemispheres. Oscillations can propagate along these lines, linking regions separated by thousands of kilometers. Observations show that signals detected in one hemisphere often have corresponding signatures in the other, with slight delays corresponding to propagation times. These delays are on the order of tens of seconds, consistent with wave speeds of several hundred kilometers per second along field lines. The system is not instantaneous, but it is coherent across global scales. There is also the influence of Earth's rotation. As the planet rotates at approximately 0.465 kilometers per second at the equator, different regions move relative to the incoming solar wind. This introduces variations in how energy is deposited across longitudes. Over time, these variations can interact with resonant modes, producing patterns that drift or evolve. This creates a layered temporal structure. Some variations occur on timescales of seconds to minutes associated with resonances. Others occur on timescales of hours associated with rotation. Still others occur on timescales of days associated with solar wind conditions. The observed anomalies are not confined to a single timescale. They span multiple layers, indicating interactions between processes that are usually treated separately. There is also a statistical perspective that reveals something subtle. When the distribution of fluctuation amplitudes is analyzed, it does not follow a simple Gaussian distribution. Instead, it exhibits heavier tails, indicating a higher probability of larger deviations than would be expected from random noise. This suggests that the system occasionally enters states where larger responses are more likely. Such behavior is characteristic of systems near criticality, where small changes can produce disproportionately large effects. The magnetosphere-ionosphere system may operate near such a state under certain conditions. This does not imply instability in the sense of collapse, it implies sensitivity. The system is poised in a way that allows it to respond efficiently to inputs, but also makes it susceptible to organized fluctuations. There is a final aspect that connects these observations to a broader framework. Plasma, the state of matter that dominates the magnetosphere and ionosphere, is inherently capable of supporting waves and instabilities. These include alpha waves, magnetosonic waves, and various drift instabilities. Each has characteristic frequencies and propagation properties. The observed oscillations align most closely with alphanic modes, where magnetic tension acts as a restoring force. These waves travel along magnetic field lines and can couple to particle motion, transferring energy between fields and plasma. The presence of these modes is not new. What is notable is the coherence and persistence observed during the March period. It suggests that the system was not only supporting these waves, but organizing them into sustained patterns. This brings the discussion back to the initial observation. The instruments did not detect stronger signals, they detected more organized ones. The atmospheric shield did not become louder in amplitude alone, it became structured in time and space, revealing modes of behavior that are present but often obscured by variability. The system, in effect, revealed its underlying architecture. And once seen, that architecture suggests that the boundary between Earth and space is not merely a shield, it is a resonant system capable of storing, transferring, and organizing energy across scales that extend from meters to thousands of kilometers. There is a further implication that only becomes clear when the data is viewed over longer intervals, beyond the immediate sequence of oscillations. When measurements from multiple days in March are aligned and averaged, the apparent irregularity begins to resolve into recurring windows. These windows are not identical, but they share a common structure. Periods of relative calm, followed by intervals of increased coherence, then a gradual decay. The cycle length varies, often between 3 and 6 hours, suggesting that the system is not continuously resonant, but periodically driven into resonance. This periodicity introduces a constraint. It implies that the system requires time to accumulate energy before entering a coherent state. Once that state is reached, it persists until dissipative processes reduce the stored energy below a threshold. To make this concrete, consider a reservoir being filled by a steady inflow. If the outflow is initially small, the water level rises. Once it reaches a certain height, overflow begins, releasing water until the level drops again. The cycle repeats. The reservoir does not remain full or empty, it oscillates between states. In the atmospheric system, the reservoir is energy stored in magnetic fields and plasma motion. The inflow is driven by the solar wind. The outflow occurs through dissipation in the ionosphere and radiation of energy away from the system. The observed cycles reflect the balance between these processes. There is also a spatial pattern associated with these cycles.
During periods of increased coherence, the strongest oscillations are often concentrated in auroral regions, roughly between 60 and 75 degrees latitude. These are the zones where magnetic field lines connect most directly to the outer magnetosphere, allowing efficient energy transfer. At these latitudes, currents known as field-aligned currents intensify. These currents can reach magnitudes of several million amperes, flowing along magnetic field lines between the magnetosphere and ionosphere. Their variations are closely linked to the oscillatory behavior observed in the magnetic field. The connection is not incidental. Field-aligned currents act as conduits, transmitting energy and momentum between regions. When oscillations develop in the magnetosphere, these currents carry the signal downward, modulating ionospheric conditions. There is a delay between the onset of magnetospheric oscillations and the corresponding ionospheric response. This delay is typically on the order of 10 to 60 seconds, consistent with wave propagation speeds along magnetic field lines. The delay is small but measurable, and it confirms the direction of energy transfer. Another layer emerges when considering the role of the plasmasphere, a region of relatively dense, cold plasma extending up to several Earth radii. The plasmasphere acts as a boundary, separating regions of different plasma densities. Its shape and extent change in response to geomagnetic activity. During periods of increased solar wind driving, the plasmasphere can contract, bringing denser plasma closer to Earth. This alters the propagation properties of waves, changing their speeds and reflection points. In effect, the length and tension of the system's resonant structure are modified. This modification shifts the natural frequencies of the system. Oscillations that were previously weak can become stronger if the system's parameters align with the driving frequencies. The result is a dynamic adjustment of resonance conditions. There is also the influence of composition. The ionosphere contains multiple ion species, including O+, H+, and He+, each with different masses and behaviors. The relative abundance of these ions affects how waves propagate and how energy is distributed. During certain conditions, heavier ions such as O+ can dominate, altering the system's response. Measurements indicate that during the March events, there were variations in ion composition at altitudes between 200 and 500 kilometers. These variations were not extreme, but they were sufficient to influence wave propagation speeds by several percent, which in turn affects resonance conditions. There is a subtlety here. The system does not require large changes to produce noticeable effects. Small shifts in density, composition, or field strength can alter how energy is organized. The sensitivity is built into the physics. There is also a coupling to the lower atmosphere that is often overlooked. Waves generated in the lower atmosphere, such as gravity waves and planetary waves, can propagate upward and interact with the ionosphere. These waves originate from processes such as weather systems and temperature gradients in the troposphere and stratosphere. As they move upward, their amplitudes increase due to decreasing density. By the time they reach the ionosphere, they can modulate densities and temperatures, providing a background structure upon which magnetospheric influences act. During the March period, there is evidence that such upward propagating waves contributed to the baseline conditions. They did not drive the oscillations directly, but they may have influenced where and how strongly they manifested. This introduces a vertical coupling that spans from the surface of the Earth to the edge of interplanetary space. Processes separated by hundreds of kilometers in altitude are linked through wave propagation and energy transfer. The system, therefore, is not only horizontally extended, but vertically integrated. There is also a temporal layering that becomes apparent when examining longer data sets. Over the course of weeks, the frequency of coherent intervals appears to correlate loosely with changes in solar wind conditions, particularly the orientation of the interplanetary magnetic field.
When this field has a southward component, it can reconnect more effectively with Earth's magnetic field, allowing greater energy transfer into the magnetosphere. During March, there were intervals where the southward component persisted for hours, creating favorable conditions for energy input. These intervals often preceded or coincided with periods of enhanced coherence in the atmospheric response. The correlation is not perfect. There are instances where favorable solar wind conditions do not produce strong oscillations, and instances where oscillations occur under less favorable conditions. This indicates that internal state and external driving both play roles, and their interaction is complex. There is also an asymmetry that emerges between day and night sides of the planet. On the day side, the magnetosphere is compressed by the solar wind, and energy input is more direct. On the night side, energy is stored in the magnetotail and released through processes such as magnetic reconnection. Oscillations can be generated in both regions, but their characteristics differ. During the observed events, some oscillations appeared to originate on the day side, driven by solar wind pressure variations, while others were linked to processes in the magnetotail. The resulting signals overlapped, creating composite patterns that are difficult to separate. This overlap contributes to the complexity of the observed data. What appears as a single pattern may be the superposition of multiple processes occurring simultaneously. There is a final observation that ties these layers together. When the system is analyzed as a whole across latitudes, altitudes, and timescales, it exhibits properties of a coupled oscillator network. Each component has its own natural frequencies and damping characteristics, but they are linked through connections that allow energy to move between them. Under certain conditions, this network can synchronize. Oscillations in different parts of the system align in frequency and phase, producing coherent behavior across large regions. This synchronization is not permanent. It emerges, persists, and then dissipates. But when it occurs, it reveals the underlying connectivity of the system. The March anomalies are not defined by a single cause. They are defined by the alignment of multiple factors: solar wind conditions, magnetospheric configuration, ionospheric state, and atmospheric background. When these factors align, the system responds in a way that is more ordered than usual. And in that order, the atmospheric shield reveals itself not as a passive barrier, but as an active, interconnected system that can organize energy across scales that extend from the surface of the Earth to the edge of interplanetary space.
There is a point where the distinction between external forcing and internal response becomes difficult to maintain. When a system is weakly driven, cause and effect appear separate. A disturbance arrives, the system reacts, and then it returns to equilibrium. But when coupling increases, the boundary between input and response begins to blur. The system does not simply react, it participates. This is what the March data begins to suggest. The magnetosphere is not only being shaped by the solar wind, it is feeding back into it. As magnetic field lines reconnect and release energy, they generate flows and fields that propagate outward, interacting with incoming plasma. These interactions modify the local conditions at the boundary, altering how subsequent energy enters the system. The process is not symmetrical, but it is continuous. Energy flows inward, is redistributed, and partially flows outward again. The system is not a one-way interface, it is a dynamic exchange. To understand this, consider a shoreline where waves approach from the open ocean. The shape of the shoreline influences how waves break, but the breaking waves also reshape the shoreline, altering the conditions for the next set of waves. Over time, a feedback loop develops between incoming energy and local structure. In the magnetosphere, this shoreline is the magnetopause. the boundary where Earth's magnetic field meets the solar wind. Its position varies, typically around 10 Earth radii on the day side, or about 63,700 kilometers from the center of the planet. During periods of increased solar wind pressure, it can be compressed inward by several Earth radii. As this boundary moves, it changes the configuration of magnetic field lines and plasma distribution. These changes affect how waves propagate and where energy is deposited. The system is continuously reconfiguring itself. There is also a timing aspect that becomes critical. The solar wind is not uniform. It arrives in structures, streams, shocks, and discontinuities that carry variations in density, velocity, and magnetic orientation. These structures can persist for hours or days. As they interact with Earth's magnetic field, they create sequences of conditions that either enhance or suppress coupling. During March, sequences of solar wind conditions appeared to align in a way that favored repeated energy input at intervals that matched the system's natural response times. The result was not a single event, but a series of events that reinforced one another. This reinforcement is key. It transforms isolated disturbances into sustained patterns. There is also evidence that the system exhibits threshold behavior. Below certain levels of input, oscillations remain weak and localized. Above those levels, the system transitions into a state where oscillations become stronger and more coherent. The transition is not gradual. It occurs over relatively short intervals, suggesting that the system crosses a boundary between regimes. Such behavior is characteristic of nonlinear systems, where output is not directly proportional to input. Small increases in driving can produce disproportionately large changes in response once a threshold is crossed. The magnetosphere-ionosphere system contains multiple nonlinear processes, including magnetic reconnection and plasma instabilities. These processes can release stored energy rapidly, altering the system's state. There is a specific example of this in the magnetotail, the elongated region on the night side of Earth. Here, magnetic field lines can be stretched and stored with energy. When reconnection occurs, this energy is released, accelerating particles and generating flows that propagate toward Earth. These events, known as substorms, typically occur on timescales of a few hours. They can inject energy into the inner magnetosphere and ionosphere, contributing to the overall variability of the system. During the March period, substorm activity was present but not unusually intense. However, its timing relative to other processes may have contributed to the observed coherence. When substorms occur in phase with external driving, their effects can combine. This creates a layered interaction between processes that are usually treated separately. There is also a spatial redistribution of energy that becomes apparent when examining global maps of ionospheric currents. These maps show patterns such as the auroral electrojets, currents that flow eastward and westward around the polar regions. During periods of increased activity, these currents intensify and shift in position. Measurements indicate that during the coherent intervals in March, the electrojets exhibited oscillatory behavior, with current magnitudes varying by tens of % over timescales of minutes. This variation is consistent with the presence of resonant modes modulating the current system. The currents, in turn, generate magnetic variations that are detected on the ground. This closes the loop between space and surface. There is also an energy budget that can be estimated. The total power input from the solar wind into the magnetosphere can reach values on the order of 10 to the 11th to 10 to the 12th watts during moderate activity.
This energy is distributed across processes, including particle acceleration, wave generation, and heating of the upper atmosphere. During coherent oscillatory states, a portion of this energy is organized into wave modes. The fraction is not large, but it is sufficient to produce measurable effects across the system. This organization of energy does not increase the total energy. It changes how that energy is distributed in time and space. There is a final layer that connects this system to a broader class of phenomena. Similar behavior is observed in other plasma environments, such as the solar corona, where oscillations and waves propagate along magnetic structures, and in accretion disks around compact objects, where instabilities and resonances shape the flow of matter. The equations that describe these systems share common elements. They involve the interplay of magnetic fields, charged particles, and waves. The scales differ by orders of magnitude, but the underlying principles remain consistent. Earth's atmospheric shield is one instance of this broader category. It is accessible, measurable, and complex enough to reveal the dynamics of plasma systems in a controlled environment. The March anomalies viewed in this context are not isolated curiosities. They are expressions of general physical processes manifesting under specific conditions. There is a boundary to what can be inferred from these observations. While measurements can capture the behavior of the system across multiple scales, they cannot fully resolve every interaction. Some processes occur at scales below the resolution of instruments. Others occur in regions that are sparsely sampled. This introduces uncertainty, but it also defines the limits of current understanding. Models can reproduce many aspects of the observed behavior, but discrepancies remain. These discrepancies are not failures. They are indicators of where knowledge is incomplete. There is also a timing boundary. The solar wind is not uniform. It transients. It recurs, but not in identical form. Each occurrence depends on a specific alignment of factors that cannot be replicated precisely. This makes prediction difficult. The system can be described statistically, but individual events retain elements of unpredictability. And yet, within this unpredictability, there is structure. The system does not behave arbitrarily. It follows patterns defined by its physical properties and the conditions imposed upon it. When those patterns become visible, they provide insight into how energy moves through the boundary between Earth and space. The atmospheric shield in these moments is not silent. It is organizing.
There is a final layer that emerges only when the system is examined as part of a larger hierarchy of interacting scales. Up to this point, the focus has been on the coupling between the solar wind, the magnetosphere, and the ionosphere. But this system does not exist in isolation. It is embedded within a broader chain that extends both outward toward the sun and inward toward the lower atmosphere of Earth. Energy begins at the sun, where magnetic fields in the solar corona undergo continuous rearrangement. These fields, anchored in plasma at temperatures exceeding 1 million degrees Celsius, generate streams and structures in the solar wind that carry embedded magnetic orientations across distances of 150 million kilometers. These structures are not uniform. They are shaped by rotation, eruption, and the evolving geometry of the sun's magnetic field. By the time they reach Earth, these structures have traveled for several days, maintaining coherence over distances that exceed millions of kilometers. When they arrive, they do not simply collide with the magnetosphere, they interact with it, transferring energy through processes such as magnetic reconnection, where field lines from different domains merge and release stored energy. This is the outward direction of the chain. The inward direction is less visible, but equally important. Energy deposited in the upper atmosphere does not remain confined there. It propagates downward through a series of processes that involve heating, expansion, and wave generation. The thermosphere, which can expand by tens of kilometers during periods of increased energy input, exerts pressure on the layers below it. This expansion alters atmospheric density at altitudes where satellites orbit, typically between 300 and 800 kilometers. Even small increases in density can increase drag on satellites, changing their trajectories over time. A density increase of just 10% can lead to measurable orbital decay over days to weeks. Below this, waves generated in the upper atmosphere can propagate downward, influencing the mesosphere and stratosphere. These waves carry energy and momentum, altering wind patterns and temperature distributions. This creates a bidirectional coupling. Energy flows from the sun into the magnetosphere and ionosphere, then downward into the atmosphere. At the same time, waves generated in the lower atmosphere propagate upward, influencing conditions in the ionosphere. The system is not a simple cascade, it is a network of interactions across scales. The March anomalies sit within this network. They represent a moment when the coupling between these layers becomes more apparent. The coherence observed in the upper layers suggests that energy transfer is occurring in a more organized manner and that this organization may extend beyond the immediate regions of measurement. There is a numerical perspective that clarifies this. The total energy content of Earth's magnetic field is on the order of 10 to the 18 joules. The energy input from the solar wind during moderate activity, around 10 to the 11th to 10 to the 12th watts, accumulates over hours to days, contributing a fraction of that total. The ionosphere, by comparison, contains energy on the order of 10 to the 15 joules, distributed among charged particles and electromagnetic fields. These numbers differ by orders of magnitude, but they are connected through transfer processes that redistribute energy continuously. The system does not require large inputs to change its state. It requires sustained inputs aligned with its internal dynamics. There is also a constraint imposed by relativity. Signals and disturbances propagate at finite speeds. Electromagnetic waves travel at the speed of light, approximately 300,000 kilometers per second. Often waves in the magnetosphere travel at speeds ranging from a few hundred to several thousand kilometers per second, depending on plasma conditions. These propagation speeds introduce delays that shape how different parts of the system interact. A disturbance at the magnetopause may take tens of seconds to influence the ionosphere and minutes to propagate across the magnetotail. These delays create phase relationships between different regions, contributing to the observed patterns. There is a time delay analogy that makes this tangible. If you clap your hands in a large hall, the sound reaches nearby surfaces almost immediately, but reflections from distant walls arrive later. The pattern you hear is a combination of direct and delayed signals. In the atmospheric system, the echoes are not sound, but waves traveling through plasma and magnetic fields. The system's response is shaped by both immediate and delayed interactions. This layered timing contributes to the complexity of the observed signals. What appears as a single oscillation may be the result of multiple waves arriving at different times and interacting. There is also a geometric perspective that connects this system to larger cosmic structures. Magnetic field lines in the magnetosphere form a network that resembles, in abstract form, the filamentary structures seen in the large-scale distribution of galaxies. In both cases, the geometry guides the flow of energy or matter. In both cases, the structure emerges from underlying physical laws rather than external design. The comparison is not exact, but it is instructive. It highlights that similar patterns can arise across vastly different scales when systems are governed by similar principles. There is a final implication that extends beyond Earth. Every planet with a magnetic field and atmosphere exhibits some form of this coupling.
Jupiter, with a magnetic field roughly 20,000 times stronger than Earth's at its surface, supports oscillations and interactions that are more intense and extend over larger volumes. Its magnetosphere spans millions of kilometers, interacting with a solar wind that varies with distance from the Sun. Mars, lacking a global magnetic field, interacts with the solar wind differently. Its atmosphere is directly exposed, leading to processes that strip particles away over time. The absence of a strong magnetic shield results in a different kind of coupling, where the boundary is less defined. These comparisons place Earth's system within a spectrum of possibilities. The behavior observed in March is one instance of how such systems can organize under specific conditions. There is also a boundary to what can be known from these observations. While the data reveals patterns and suggests mechanisms, it does not provide a complete description of every interaction. Some processes occur at scales that are not directly observable. Others depend on parameters that are difficult to measure precisely. This introduces a form of incompleteness. Models can approximate the system's behavior, but they cannot capture every detail. The remaining discrepancies are not errors to be eliminated, they are indicators of where understanding is still evolving. There is also a time limitation that captures a finite interval, measured in days and weeks. The system's behavior over longer timescales, years, decades, or centuries, may include patterns that are not yet visible. The March anomalies are a snapshot within a much longer sequence. And yet, within that snapshot, the system reveals something fundamental. It is not passive, it is not uniform, it is capable of organizing energy into coherent structures that span multiple layers and scales. The atmospheric shield is not simply protecting Earth, it is participating in a continuous exchange with its environment, shaped by forces that originate at the Sun and propagate through space, and by processes that arise within the planet itself. And when the conditions align, that exchange becomes visible, not as a sudden event, but as a pattern that emerges, persists, and then fades, leaving behind a trace of how the system works.
There is a moment, just before the pattern fades, when the system becomes most legible. The oscillations are still present, the frequencies remain aligned, the delays between layers are measurable and consistent. Energy continues to move along magnetic field lines through plasma into the atmosphere below. But the amplitude begins to decrease. The coherence weakens. The structure that held the system together starts to dissolve. It does not stop abruptly, it unwinds. What remains in that transition is not noise, it is the residual imprint of organization, evidence that for a limited interval, a system spanning from 100 kilometers above the surface to tens of thousands of kilometers into space behaved as a single coupled entity. This is the climax of the observation. Not a peak in intensity, but a peak in clarity. The atmospheric shield, often described as a barrier, reveals itself as something else entirely. It is a dynamic interface that stores energy, redistributes it, and under specific conditions, organizes it into coherent motion. The anomalies observed in March are not deviations from normal behavior. They are instances where the underlying behavior becomes visible. The discrepancy is not between expectation and observation in magnitude. It is between expectation and observation in structure. The old model assumes that variability averages out, that fluctuations remain largely independent, that the system returns to equilibrium without revealing its internal architecture. The new observation shows that, at times, the system does not average out, it aligns. And when it aligns, it exposes how deeply connected its components are.
There is a final implication that extends beyond this specific event. The processes observed here, resonance, coupling, threshold behavior, feedback, are not unique to Earth's atmospheric environment. They are fundamental to plasma systems throughout the universe. The same principles govern oscillations in stellar corona, interactions in interplanetary space, and energy transport in astrophysical plasmas on scales that exceed entire solar systems. What is observed near Earth is a local instance of a universal pattern. And yet, there is a boundary that remains. Even with synchronized measurements, precise timing, and global coverage, there are interactions that occur beyond the reach of instruments. Some processes unfold at scales too small or too distant to resolve. Others are masked by overlapping signals that cannot be fully separated. This is not a limitation of effort, it is a limitation imposed by the system itself. We observe the patterns when they emerge. We infer the mechanisms that produce them. But there are aspects of the interaction between Earth and its space environment that remain partially concealed, not because they are rare, but because they are embedded within layers of complexity that cannot be fully disentangled. The atmospheric shield is not silent. It is continuously active, continuously exchanging energy, continuously adapting to conditions that originate far beyond the planet. Most of the time, this activity appears irregular, fragmented, indistinct. And then, briefly, it organizes. In those moments, the system becomes visible, not as a collection of separate layers, but as a single structure extending from the surface of the Earth into space, shaped by forces that connect a planet to its star. The signal does not announce itself. It reveals itself. If you liked the video, do not forget to leave a like and subscribe. It makes a huge difference and helps the channel grow.